So for Lab 7, we're going to start the discussion with a review about backlash. What backlash is the gap between the lead screw and the nut on the surface that we are trying to control. To take it a step back, in order for two parts to be assembled, you must have some clearance between the two parts. You can't make two parts the exact same size and expect them to fit together. If you were to make a 1/4 inch diameter hole, for example, and try to put a 1/4 inch diameter pin in it, it won't fit. One has to be a little over and one has to be a little under. So you have to have some room in there for the two parts to physically fit together. When you have a lead screw and a nut, or a regular screw and a nut like from Home Depot or Lowe's, one of those is bigger than the other. And that's just so they will physically fit together. The same is true on the machines. In order for the nut that drives the table back and forth to have a lead screw fit through it, it has to be a bit oversized. And that presents a little bit of a problem for us when we're working on manual machines. Manual machines are also called conventional machines. And when we are operating them, we are operating them by hand. So we are physically controlling how fast we move back and forth the table, and we are also controlling the position. We control the position on the machines by adjusting the lead screw. So when we turn the screw in one direction, it moves until it engages the nut, which is attached to the table, and pushes the table in that direction. If we turn around and turn that screw the other direction, there's going to be a moment where that lead screw is not actually in contact with one of the sides. And so you'll be able to turn the lead screw, and if you're looking at the dial that has the numbers on it, it's going to tell you that you're moving, but you're not actually moving the table because you're not in contact with the nut. And this phenomenon is called backlash. I have a demonstration here that will hopefully help to illustrate what's going on. This red section that I've got colored in here represents the gap between the nut and the lead screw. And if we turn the lead screw handle, it will pull it. And you'll see that until we make contact with this, it won't actually move the nut. So you can see I can move the lead screw back and forth. And there are moments when I'm going back and forth that it's not driving the nut or the table in any direction. It's just floating in between there. And that floating in between there is the backlash. Now, how do we prevent the backlash from affecting us? Well, if we work in one direction all the time when we're talking about taking a measurement. So if we read the dial and we say we're going to move 20 thousandths, and we want to move another 20 thousandths, you can't go 20 thousandths in this direction and then go 25 thousandths in that direction and then say, whoops, I went too far, and then back off 5. That doesn't work, because what happens is you move forward, then you move forward too much, and then you said, oops, I went too far, and then you come back. The table stayed where you left it, and you move back. Now, the dial is going to say that you're in the right place, but you're not, because you turned around and came back. So how do we prevent that? Well, there's two ways. One is you just always work in one direction and you only read the dial in one direction. So that's one of the principles of using a manual machine, is that you're only working in one direction whenever you're taking a measurement or moving to a position. What if you go too far? Well, that's okay, it happens. And what you do is you go back further than you meant to, and then you go back and reset your position moving in that same direction. You just have to physically go back past the amount of backlash on your machine. I typically tell people to go one full turn, because there's no way that there's one full turn on the handle of backlash. It's different on every single machine. So we have to make sure that we understand that concept. We have to make sure that we operate within the confines to prevent backlash from having us position things in the wrong position. It's very tempting to dial and then go just a little too far and then just back up just a little bit and be like, yep, I'm in the right spot. It doesn't work. You have to, if you go too far, you have to turn around, back up, and then reapproach. When we're milling and we're using the side of an end mill, we're going to call that side milling. And there are two types of side milling that are options for you to choose from. You have climb milling, and then you have conventional milling. When we're climb milling, your material feed is feeding in like this. And these are top views, okay? And so your end mill is on one side of the material, and you're going to feed the material past the end mill. When we do that, your cut is right here, like that little green chip. That's going to be the piece of material that gets cut out. And so the resultant force created by that cutting action kind of follows these little blue arrows here. We have that right there. To get the material to move, we have to act on it by pushing on it with a force, right? And if we take a look at the sum of the forces on a free body diagram, we can start to see the effect on that piece of material. We have to go through a couple of assumptions though. When we're side milling, a couple of the assumptions that we need to make. One is that we need to prevent motion in this direction, right? We achieve that by using the table locks on the machine. That will prevent that motion in that direction. So we need to make sure that we set our table locks in this feed direction. The other thing is that we're going to prevent any rotation of the part, right? We can't have the part rotating like this, and we do that by securing the vise to the table and securing the part into the vise. And so that's going to prevent that. So if we start to look at some of the forces, we can ignore the things in the assumptions that we want to ignore. So we can ignore the vertical components of things, and we can also ignore what might look like a moment type of force. So if we look at the cut force, we have this arc type of resultant force. If we take the vertical components out, if we take all of those components out, and any of that rotational type of component out, what we're left with is a force that is pointing to the left right here. And if our material feed is feeding to the left, and we add that to a free body diagram, what we'll see is that we have the cut force and the feed force in one direction, but nothing really opposing that force. Now there is a force that lives over here, but we don't know what it is. And I don't mean that it's a mystery. I mean we have no way of actually calculating or figuring out or changing what that force value is. What it is the force due to friction. All right? So this unknown is the force due to friction, and the reason it's an unknown is because it's different for every workpiece, every machine, the condition of every machine, the age of every machine. There's so many unknowns there, right? So it does exist, but it's an unknown, and in the grand scheme of things, it can be small compared to the sum of these two. Another thing that we need to know is that these two forces, the cut force and the feed force, are tied together in a dynamic feedback loop. And it's a proportional feedback loop. What that means is that as I feed the material harder, that resultant force from the cut gets bigger. So this gets bigger, which makes this bigger, right? If we overcome this by the sum of these two, we can basically say that it goes away. We start to get motion. And when we get motion, the feed force gets bigger, which makes the cutting force get bigger, which makes the feed force get bigger because they're in a feedback loop. One affects the other and makes this one bigger, this one bigger, this one bigger, this one bigger. And so they both start growing. And what you end up with is a situation where you have runaway. And what happens is that this thing starts to move on its own because of this feedback loop. Now, does that mean it's going to go flying across the room? No, because it is secured to the table and everything. So what's allowing it to move? Well, what's allowing it to move is the backlash. So what it will do is it will jump forward by the amount of backlash until that nut hits the other side of the screw, and then it will stop it from moving. The problem with that is that if you're trying to control a dimension and this thing's moving on you, you don't know where you are and you can't control the actual position. And that's a problem. The other problem is that when you start having this thing jump, your load on your tool or your feed per tooth starts to change and grow, and you get other stability problems. So that's climb milling. So on a manual machine, climb milling is somewhat problematic for us. Now, does that mean that you cannot climb mill? No, it does not. So how would we go about climb milling on a conventional machine? Well, what we have to do is we have to make sure that the force resultant due to the cut and the feed force stay low enough that they will never oppose that force due to friction over here that is an unknown force. We know it's real, but we don't know how big it is. So it's a little bit of a gamble, to be honest with you, because the newer, more lubricated, better in shape machine that can float the table a little easier is actually more susceptible to these two forces overcoming that force due to friction. But it can be done, and we do it all the time. But what you end up having to do is we have to reduce the radial depth of cut. So if you want to climb mill on a conventional machine, you have to take very, very tiny radial depths of cut, which is this distance. How far radially you have moved the tool into the part. Because as this goes to zero, this goes to zero. I hope that that makes sense. So as this depth of cut gets smaller and smaller and smaller, then your force of your cut gets smaller and smaller and smaller. Likewise, as our material feed force gets smaller and smaller and smaller, basically you slow your feed rate down, which means that you're applying a smaller force for the feed, then that gets smaller as well. So these forces shrink up, and this force that actually is a resultant force coming from those that is a reaction force can oppose it and prevent that motion. So that's climb milling. Now for conventional milling, the thing that changes is the direction of the material feed. So instead of feeding the material like this, we're now feeding the material like this. So we're still on the same side as we were for our climb milling example. The cutter is still rotating clockwise from the top down, just like before, but the difference is we have changed the material feed. So what does that change? Well, it changes our assumption of our sum of forces. We still have to say we're not allowing any of the directional forces to be included in this analysis for right now because of the table locks, and we're still not going to allow the part to rotate because we've got it in a vise and have it bolted down securely. So when we go to the free body diagram, what we end up with is a potentially more balanced system. So we've got feed force opposing the cutting force. Well, that's good. That's real good, because these are still in a proportional block, right? They are still proportional to one another. They still have that feedback loop. But now if I have a big feed force, I have a big cutting force. And you'll get to a point where your feed force overcomes your cutting force, and at that point in time, you actually start cutting material. That's what we hope is going to happen, is that our feed force gets bigger than our cutting force, and we're actually cutting material. And that's how that works. So on conventional milling, whenever we stop feeding, this force goes away. With climb milling, if the sum of those two forces is larger than the friction opposing it, it can keep moving. And that's the problem with climb milling on a conventional piece of equipment or manual equipment, is that it's possible when you're climb milling for the material to keep going. With conventional milling, when one stops, the other stops. So if I send my feed rate to 0, my cut force goes to 0 because they're proportional to one another. So we're tied to conventional milling. Another type of milling that we are going to use in the shop is end milling or edge milling. I've heard it called surface milling. They're a variation of a full slot milling operation that we'll talk about here in a moment, but it's when the tool is going over the top of a surface and you're taking material off of the top of a surface. Now, if your workpiece is narrower than the tool is, we have this scenario where our tool is a bigger diameter than the width of our workpiece. You'll see this a lot of times if you're taking a piece of material down to size, for example. One of the things that is relatively important to keep in mind when you're doing this, in order for our assumptions to make up, you need to have that workpiece relatively centered under the tool. If your workpiece is relatively centered, we have our feed force, we've got our cutting force, which will be balanced. All of our vertical components will be balanced because we can't lock the feed rate in this direction because that's the way, or we can't do the table locks in this direction because we've got our feed in that direction. But we can lock the table locks in this direction, so we can prevent motion in this direction. And so we would like to have a predictable output, a stable free body diagram, something that is not containing unknowns. So the only way we can really do that is to make sure that this workpiece is centered. Because if we do that, this is what our free body diagram looks like. We'll have our feed force. We'll use our table locks in this direction to prevent any motion. And our resultant force from our cut, we'll push on it like that. So we're feeding it like this, pushing on it with the cut like this. The table locks are resisting this motion. And what we're left with is these two forces here balance each other, because the bigger this gets, the bigger this gets, because it's a resultant force that is equal to this. And we're left with a feed force right here, which means that we're going to have motion. Well, that's what we want. We want that part to go up underneath the cutter so that we can actually cut the part. Now, what happens if you slide this part over to one side or the other is that you either get climb milling or conventional milling. If you're on this side and you feed here, you will get components that aren't balanced, because when we're centered, we have a component here that matches with a component here. So the vertical components always match if it's centered. If we slide to one side, we start to get all components going one direction in the vertical. And what we'll end up with, if we're on this side over here, we'll end up with a portion of the cut resultant force going down here and pairing up with the feed force. So that means that feed force and cut force have a component that align. So if we're off on this side, it's climb milling. If we go over to this side, they oppose. So if we are off to this side, then we're conventional milling. So you need to keep that in mind. If you have a reason to be off to one side over your tool, then you need to pick the side accordingly. This side over here will be conventional milling. This side over here will be climb milling. Slot milling is whenever we are going to have a workpiece that is wider than our tool, and the tool is going to get submerged below the surface and cut a slot or a groove down inside of the material. We have a piece of material that is passing in this direction, and the tool is smaller than the material itself feeding down into it. So it's cutting equally on both sides of the cutter. So all of the vertical components are matched on the left and the right. So they're going to cancel each other out as we feed the material beneath that tool. So whenever we do the sum of the forces, what we're going to get with our cut force is a force that points to the left. There won't be any vertical component there because our prior assumptions are still in place. We're not going to allow any of that rotation. Now we have to allow movement in this direction. We won't allow movement in this direction now. So how are we able to not allow movement in this direction? Table locks. Remember, we have a resultant force by using our table locks to prevent this thing from moving, because if you don't, what you'll get is a slot that looks like an S curve. So your table locks, whenever you're slot milling, are super critical. So we've got our feed force pushing the material up, a resultant cut force by our feed, and a resultant force that is overcoming the force on the side from the cut force. So what we end up with is the free body diagram that moves up, and that's what we want. We want our material to move beneath the tool. This is a dial indicator, and a dial indicator is a measurement tool that we use in the machine shop, and it allows us to get relative measurements. Relative meaning that it's not going to tell us if something is 1 inch, for example. It's going to tell us that from a set point, another measurement that we take relative to that set point deviates by a small amount. One of the advantages to using a dial indicator is that we have all sorts of flexibility in the orientation of the measuring tool. Now, how this thing works, there are a couple of pieces that we're going to talk about. We've got the dial, and the face on the dial rotates. And it rotates so that we can adjust our set point. Now, a lot of times people at rest will point the 0 to where the needle rests. You'll hear me refer in a lot of my discussions to set the 0 opposite or approximately opposite of where the needle rests. And there are advantages to both of those methods. So that's the face. We've got the dial right there. Each one of these tick marks, if you look on the face of this dial indicator, Each one of those tick marks is 0.0005 inches, or 5/10 of a thousandth, or a half a thousandth. So this is a half thousandths indicator. Each one of these tick marks is a half of a thousandth. So every other one, and you can see on here, one's a little short, one's long, one short, one's long, one short, one's long. So each one of the long marks, or every other mark, is 1/1000th of an inch. And so you can count them through, and you can say half 1, half 2, half 3, half 4, and then half 5. And you've got 5, 10, 15, and then it goes back down. And the reason it goes back down is because you may be using one side or the other of the needle. Now, the needle is this portion right here. This thing works by deflecting the needle. That needle rotates about this point right here. We can adjust the position of that needle by gently pushing it to its extent and continuing to push it on around. Now, this is a little unnerving the first time you do it and the first time you handle it, because it's going to feel like you shouldn't be doing that. But that's how it actually works. You just push it, it'll get to its end point, and you can rotate it around. At the end of the needle here, we've got a ball. And that ball is what's going to come in contact with the material that we're actually measuring. You want to make sure that the ball is the only thing that comes in contact with the surface that you're measuring. That's very important. Another piece that we are interested in is the dovetails on the dial indicator. I'll show you on a different indicator where these guys come in real handy. This is the stem, and on this style of indicator, you can hold on to the stem, and you can grab this stem of the indicator in a vise of some sort. You can grab it in a drill chuck. They make holders that grab onto the stem. So there's all sorts of different things you can do. And what we can do then is we can adjust the position of this thing to match up with whatever it is that we want. And then whenever we deflect the needle, the dial is going to move around. Now, they're very sensitive, and just barely trying to touch it, you can see that it's difficult to get the dial to move slowly because they're very, very sensitive. And speaking to that effect, these things are extremely shock sensitive. What I mean by that, don't drop it. They're very fragile. Okay, think about it like a really expensive, fine crafted watch. You wouldn't take a Rolex and drop it on the concrete. You could destroy it. So this isn't as expensive as a Rolex, but they are very expensive. This dial indicator here costs somewhere in the neighborhood of $125. And it is, I would argue it's at least as fragile as an egg. So you want to use some care whenever you're handling it, and make sure that you don't drop it or something like that. Now, if you were to drop it like I have it right here down to that table, it's probably going to be fine. It'd be like an egg. If I dropped an egg that far, it's probably going to be fine. But if I raise it up, the further I get, it's more likely that something bad's going to happen. And especially if I drop it onto the floor, you're probably going to end up with a mess. So please handle them carefully. Now, going back to the dovetails, this is a different style of indicator. It does not have a stem on it, you can see, but it has a dovetail on the top. It's got a dovetail on the back, the front, and the top right there. And this is a dovetail holder, and there's a small screw that goes in and out of this dovetail cutout here. And so if we unscrew it, we can slide the dovetail in there, and then we can tighten it. And now this allows us to have a stem on this style of indicator. And this indicator works the same way. Got the needle. You can adjust the needle like that. If you have questions after you've started using the dial indicator, it does take a little bit of practice, but if you have questions, talk to your TA or one of the lab instructors. When using a dial indicator, one of the first things that we'll talk about is the calibration angle, or the optimal position whenever we're speaking about the angle that the needle has with reference to the surface you're measuring. So if we were to talk about measuring this vertical surface here, we're going to have an angle of 12 degrees off of that surface, away from that surface. That's going to give us room for the needle to deflect, as that surface may move in this direction, in order to give us a measurement. So the calibration angle is our optimal measurement angle. Now, you can change that angle and still get a measurement, but the calibration angle is where the indicator is certified at. So if we can shoot for that 12-degree angle, it's going to be the most accurate. Now, you don't need to get a protractor out and try to set it exactly to 12 degrees, but what we want to avoid is a situation where we have extreme angles, such as this right here, where we're at 0 or even worse than 0, because if we get to the point of where we tip past 0, the shaft of the measurement needle can come in contact with the corner of the part, and the ball actually comes away from the surface we're measuring, and now we don't know where we're at all, because you're measuring some other weird thing that it's not good. So you want to avoid this altogether. And another thing you want to avoid is having an angle like 90 degrees, because whenever you have that angle, this needle can't rotate. Remember, whenever we were talking about how the indicator actually functions, this needle must rotate in order to give us a value. And if it's like this, if this surface moves, it's actually going to push the body of the indicator around, right? So we need to avoid these two especially. Now, we could take a measurement with the indicator in this position, but not of this surface. It would be measuring the top. So if we needed to measure the deviation of the top of the surface, we may actually have a situation where the indicator looks like this, but it then would probably need to be angled down just a little bit, and we would position the ball on that top surface, and we would end up having some version of this drawing right here, right? So don't get tied into this being what the picture looks like. Recognize that this angle setup is what we're talking about, because that's what's important. When we're using a mill, many times we're going to want to use a vise to hold our parts. I've drawn a simple schematic up here of a mill vise and how we have to align the mill vise in order to achieve certain goals whenever we're milling parts. We have a fixed jaw on the vise, we have a moving jaw on the vise. We're always going to take measurements and refer to measurements being taken from the fixed jaw, because it doesn't move once the vise is bolted down. We're going to go over the steps involved with aligning the mill vise to the axis of travel that we want. Now, this axis of travel can turn and the vise can turn with it, doesn't matter. Or you can actually align it to a specific angle. So if you had a 45-degree block or something that you wanted to set as your alignment so that the vise was actually set at 45 degrees, you can do that as well. The steps are all still the same. So we have our fixed jaw and our moving jaw, and I've just labeled sides A and B. These are feet that nuts go over to bolt the vise down to the table, and this back here is the handle that turns and moves the moving jaw in and out. And at the back of the vise is where we're going to actually tap on the vise with a dead blow hammer to make some adjustments here in just a moment whenever I'm explaining it. So our axis of travel is right here. Our axis of alignment is this fixed jaw, or that red line right there. So we're going to go through the steps involved with aligning a mill vise. So the first thing that we're going to do is, I've got an example side over here, and then these are the steps. So we're going to pick a side to start from. That's the first thing you do, and it does not matter, but that's why I put the example over here. So we're going to pick a side to start from, and we're going to pick side A just for this example. And the next step is loosening the nut on the opposite side and tightening the nut on the starting side. So we started on side A, so we're going to tighten the nut on side A and loosen the nut on side B. Step 3 is we're going to use a dial indicator on the fixed jaw and set a 0. So we're going to have a dial indicator sitting right in here, and we're going to move the vise toward the indicator and set a 0 point on the dial indicator. The next thing we're going to do is we're going to measure across to the opposite side. So remember, whenever we're milling, we're always moving the material or the table or the vise. We're not moving the spindle. The spindle stays still on a conventional machine. So we're going to move the vise around, and so we're going to measure across to the opposite side. So the first thing we did was we moved the vise down to where the indicator reads 0, and then we're going to move the vise across so that we can measure that fixed jaw. When we do that, we are going to see the dial indicator needle move. And whenever it moves, we know how far it is from one side to the other away from 0. So we're going to use a dead blow hammer or a soft hammer to tap on the vise to adjust out that difference. And we're going to go to the machine so that you can see how to tell which direction you should tap it and everything. So that will become more apparent whenever we actually work through an example on the machine. So we're going to use a dead blow hammer to tap out the difference. And then we're going to move the vise away from the indicator. So this is a key step. So we're over here and we left the vise touching the indicator, and we're going to tap around. And the reason we leave it against the indicator needle is so we know how far to tap it, right? So we're tapping it, and we'll get the indicator needle will move, and so we'll adjust it back to where it's close to 0. And then we're going to move the vise away so that the indicator needle is not touching anything now, and we're going to move the vise back to where we're back to that starting side. So we move the vise away from the indicator and return to the starting side. Then we're going to move the vise toward the indicator, stopping at the 0 that we set earlier on the indicator. So basically that step is going to look like this. We're going to measure across, we'll be up here, tap out, and then back to our 0 again. At that point, we're going to repeat steps 4 through 7 until we get the vise aligned to our liking. Okay, so we're just going to measure across, tap around, go back to the beginning, measure across, tap around, go back to the beginning, and so it's just an iterative process. So once it's aligned, we're going to tighten the opposite side nut. So in our example, we would then be tightening the B side nut. So now A and B are tightened up. And then we're going to measure across to the opposite side to verify our alignment. So we're going to go up, across, tap it around, back, go across, tap it around, go back until we are verified that we're aligned. Go back over here, tighten everything up, read across one more time, and that will tell us if it moved when we tighten the nut. So that last move after everything is tight is just a verification move that we are still aligned after everything is tightened up. This is lab 7, the intro to the mill. This is a milling machine. The key difference between the milling machine and the lathe is that the milling machine, the tool will spin instead of the workpiece as you saw in the lathe. I'm going to go over the parts of the mill as we go through this, starting at the top of the machine, working our way down. This is the motor on the mill. It's on the top of the mill. This piece right here, you can see that spins around, is the spindle that goes through, that is driven by the motor. On top of the spindle on a mill, you'll see this rod. Now normally this rod will live where it sits. You won't really ever take it out. But in order for you to see what it is essentially a very long bolt. This is called the drawbar. And the drawbar allows us to attach tool holders into the spindle. Now I'm going to set this back in place, and we'll go through how to attach a tool to it in a few moments. This handle right here that moves backward and forward like that is a brake. As the spindle is turning, you can push this handle and it will stop the spindle from turning. Now you only want to do that when the power to the machine has been turned off. This switch is the power switch. It is an 8-position switch on this particular model of machine, and it is labeled as, starting from the top and working our way counterclockwise, off, forward high, off, forward low, off, reverse low, off, reverse high. Now, forward and reverse are a bit arbitrary in the grand scheme of things, but for our lab purposes on these machines, you always want to run the spindle in forward high or forward low. All of the tooling that you will ever use in here is going to run in the forward direction. Now, forward direction, if you remember when we spoke on the lathe, is clockwise. And again, that is defined as clockwise on the outside of the machine on the motor end, which is the top portion here, looking down the spindle. So clockwise would be like that. So if we turn it on, you'll see in the forward direction it is spinning clockwise. I'll do that again. Just bump the spindle so that you can see it spin. And you can see it spinning clockwise. As we move down the machine, we'll get to this handle right here. And this is the quill handle. And what the quill is, it's a housing for the spindle to let the spindle move up and down. So the spindle can move up and down inside of the quill. And this handle allows you to move the quill up and down. If you've ever used a drill press or seen a drill press in action, think of it like that. That's kind of what it does. It moves the spindle down so that we can drill holes and operate different tooling different ways. This handle right here is a quill lock. We can pull the quill down into position and lock that handle down, and now the quill stays in place. If I release it and don't hold that, you see that the spring retract pulls the quill up. Be careful if you have the quill down that you don't put your face or anything anywhere near that, because that handle can whip around and can be a mild safety concern. This knob right here is called a Quill Stop. If we bring the Quill Stop up, you can see when I move the Quill Handle down, this portion right here is mounted onto the quill, and if I pull it down far enough, I can hit the Quill Stop. That allows me to position an end stop position for my quill, and as we move further on in the labs using the mill, you'll see the advantage of using the Quill Stop. This nut below the Quill Stop is just a lock nut so that you can double nut and it will hold the position of the Quill Stop and prevent it from moving around up and down. As we move down a little bit, you'll see this is the quill that we spoke of, and below here is the spindle nose, and the spindle nose has a taper in the bottom of it, and that taper for our milling machines and most standardized milling machines that are manual machines are an R8 taper. That's just a standard designation for that taper size. Moving down, this piece right here is a Mill Vise. The Mill Vise, as you could probably figure out, holds our material that we're going to be cutting. It's operated with the handle back here, and one of the things that we'll be discussing today is that it is bolted to the table. Now, we have these plywood covers on the tables, and they are held in by friction fit plastic sleeves. And the only reason that we use these is to protect the mill table. You can take them off to move the vise back and forth. You can mount parts directly to the mill table, but in general, you'll likely see a vise in use on most milling jobs. And so to prevent damage from the table, if someone sets a piece of metal or a toolbox or something like that on there, these just serve to protect the table. Going down, we have the XY axis controls. I can turn this handle and it moves me in my Y axis, and this handle moves me in my X axis. You can use the other side of the table, has a handle on it as well. It doesn't matter which handle you use. However, once you start to use a handle and set your locations, you need to stick with that handle, and we'll talk more about that as well in the future. Moving on down, we've got this right here. Now this handle right here controls our Z position of the table, and it moves this entire assembly up and down. That assembly is called the knee, just like on your body. The knee, and this is a knee mill. If I turn it clockwise staring at it, it raises the bed, and if I turn it counterclockwise, it lowers the bed. I would suggest that you pull this handle out and turn it around. That keeps you from hitting that handle, which could cause you an issue if you bump it after you've set a height or something. One of the things that you will need to know how to do is to change the RPM on the mill. This style milling machine has a belt and pulley system, and in order to change the RPM, what we do is we physically move the belt from one set of pulleys to another. This diagram on the side illustrates what the RPM available with the different switch position. For example, if the belt is on the 1-1, pulley position, we can look in the chart and see that if we put the switch in the low position, we get 775 RPM, or if we put the switch in the high position, we get 1550 RPM. To access the belts to change them, we lift this cover off, and on the inside, what you'll see is the belt right here and the different stepped pulleys that are available for you to change into. Now, in order to move the belt up or down, what we have to do is release tension on the belt. This is achieved by loosening the nut here with the 3/4 inch wrench. You do not have to remove the nut, just loosen it. And we will physically pull the motor forward, and you can see at that point we have released the tension on that belt. The method that I use is I will put the wrench on top of the drawbar with something in the spindle already tightened up, such as the drill chuck like I have right now. And I will use this wrench to rotate the spindle around to help facilitate rolling the belt onto the next pulley. To change the belt position, you are always going to choose the side of the belt pulley combination that is going to move to a smaller setting first. So if I move this belt down, for example, if I move it down on this side, this goes from a smaller pulley to a larger pulley, which means that I need to start on the opposite side. I need to go from this side, which is a larger pulley, to a smaller pulley. And so I will pull the wrench around like that, and I will manually pull the belt down and use the wrench up here to roll it around to that next pulley position. Now I work my way back to the other side by repeating the same process, only in reverse, and that allows me to change the belt pulley position. Again, I'll illustrate this. I'll go down one more. I push it down and then come back, and that simply allows me to roll the belt onto the next pulley. When I'm ready to tighten the tension back on the belt when I am at the position I want to keep, I push the motor backwards, and just by hand I'll tighten this nut, and then I'll use the wrench to tighten that nut, and I can see at that point I have a properly tensioned belt. Before I turn the machine on, I will replace the guard, and now we have moved the belt position into the 3-3 position, which would allow me to select, on this example, either 305 RPM or 610 RPM. Now, the RPM that you choose is going to change with each operation that you do. This was just an example. So when you're moving the mill tables around, sometimes it's important that we lock the table in place. The table locks for each axis are on a small handle that looks similar to this, and you tighten them in place. For the x-axis, for example, it's right there. If I move the handle, it's tight. If I loosen them, I can move the handle freely. If you walk up to your machine and attempt to move the handle and it feels very stiff, stop and check the table locks, because chances are someone left the table locks engaged. Likewise, when you walk away from your machine after you're finished using it, please check that you have released all the table locks so that the next person doesn't encounter this problem. One of the other things that we need to do on a regular basis when we're operating the mill is to adjust our zero set point. And a lot of times we will just refer to this as setting our zeros. And this occurs with this small mechanism on each one of these handles. If you look, there is a small threaded ring that goes back and forth, and we can loosen it and turn the dial that has the numbers on it to whatever value we want and tighten that ring back up, and there's a little indicator here that allows us to set that to whatever number we want. Normally we'll just set it to 0 because that's a convenient place to go to. And at that point now, that will follow this. It's important that you remember to tighten that ring back up, because if you don't, what can happen if it's left loose is that it can float as you're using it, and the 0 position will float around, and that's definitely not desirable because you don't know where you're at that point. So make sure that that ring is tight whenever you're reading the number values on the machine. So there are different types of tool holders that we will be using during the lab. There are two in particular styles of tool holders that we will use to hold end mills. A collet style, and this is an R8 style collet, and that just refers to the shape of the collet itself. And we have a set screw style end mill holder. The collet style is drawn up into the spindle and clamps very evenly around there, and will grab a hold to the shank, or this solid portion of the end mill. Now, one thing about these different end mills is you may or may not have a flat ground on your end mill. If you do, what you would like to avoid with a collet is clamping it in the flat. And by that I mean like that right there, where the edge of the collet clamping is in the middle of the flat. So you would want to go either below it or above it, but above it you start to run into problems with too much overhang, and we'll talk about that. Really, you want to limit that to about 3 to 1, which is 3 times the diameter of your cutter over length there. So this is a 3/8 cutter, so I would want 9/8 or 1 1/8 being about the maximum, and that's a bit longer than that, and you can run into tool stiffness issues. So I'd want to shorten that up. Now, with the set screw style end mill holder, first things first, you must have a flat ground on your tool in order to use this, because the way it works is you insert the tool into the tool holder and you use an Allen wrench or a hex key to tighten down on the flat, and you have to work it a little bit, and you will get that flat to where it lines up with that Allen key, and you can tighten it up. Now, I normally will have this in the spindle when I tighten it, because that gives me a lot more leverage. But you can see you're kind of limited as to where the position of the tool is based off of where the position of the flat is. So that's one limitation of this style of tool holder. Another style of tool holder that we will use all the time is a drill chuck. Now, this is a keyless style drill chuck. What you may see on a lot of hand style drills, you may have seen a chuck like this where you don't have to use a key. You just turn the end of it and it allows the jaws to open and close, and a drill bit goes in the end of it and you can clamp it down. We do have some chucks that are keyed chucks, but I won't want to go over those right now. We'll talk about those on a one-to-one basis. And those are the tool holders that we're going to use in our lab in the mill. So whenever you show up to operate the mill, you will have a mill assigned to you. You will go to the key box, get your mill key, And you will come over, and one of the first things you're going to want to do is unlock your toolbox. And you'll be able to get tooling that you need out of the different drawers. Now there are a couple of things that we're going to need. Some wrenches and tool holders, and I'm going to get those out real quick. As well as a dial indicator, which we spoke about earlier, and the drill chuck. To install the drill chuck into the spindle, the first thing that we want to do is always wipe it off to make sure that it is free of dirt, debris, and chips. We always want to make sure that any mating surfaces that we put together, we clean them so that they don't have debris in between them. Inside of the spindle, if you were to reach your finger up and feel inside of there, there is a key, a drive key, that has to align to the key slot on the tool holder. And so what you'll do is feel up in there and you'll rotate it until it hits. Now what I do is I push the tool holder all the way up inside once I engage that drive key, and then I'm going to tighten the drawbar by hand just until it's tightened by hand, and then I'm going to use a wrench, which this is a 3/4 wrench, and I'm going to turn it clockwise, looking from the top down. Now if I do that, you'll notice that the spindle is turning along with it. The way that we prevent that is we use the brake. This is one of the times that the brake is to be used. So we'll hold the brake and turn our wrench, and we will repeat that until the drawbar is tight. Now we have the drawbar mounted into the spindle, or the drill chuck mounted into the spindle. We can now install different tools like drills or countersinks or an indicator, which is what we're going to do here in a moment. I need to find out if the vise is squared to the table. If you think about the orientation of this vise, the tables move in 90 degrees. If I move my Y handle, it moves straight in and out like this. If I move my X handle, it moves straight back and forth like this. If I have my vise mounted at 45 degrees, for example, then my part, XY, is essentially going to be rotated by the angle that the vise is rotated. So if I want my X, Y, and Z coordinates to be aligned with one of the edges of my part, then I must have the vise aligned to one of the axes of travel. And that's what we're going to do. The first thing I want to do when I walk up to my machine is verify that the vise has been bolted down properly. Just check these bolts on either side of the vise to make sure that they're tight. We can then install the indicator into the drill chuck. Now, I want to take a moment to speak about the dial indicator. This is a very fragile tool. This is a measurement tool that gives us relative measurements. Relative meaning it doesn't tell me that something is an inch long. It tells me that when I take a measurement and set a set point on one side of the machine or the vise or wherever I'm making contact, if I go in a straight line to another portion, it will read out some difference by pressing on this needle. Now we'll have talked about that at the board, so hopefully that will make a little more sense now that you actually get to see it in person. In order to put this style of indicator into the drill chuck, we need to affix it to some sort of holding device. This particular device attaches onto the dovetail portions of the indicator. If you can see, that portion has a dovetail cutout on it. It slips on, and we can tighten it on like that, and now we can hold this indicator like that in the drill chuck. I'm going to use the brake to hold the quill and the spindle still, and I can use my other hand to tighten that chuck. And now you can see, if I rotate the spindle, the indicator is held in there, and what this holder allows me to do is position my indicator. What you want to avoid is turning the indicator in the spindle. You want to always just use the spindle to turn it, because if you turn the indicator, what you can see happens is you will loosen what we put together, and you'll have to retighten it up. So if you want to rotate the indicator, you need to grab it up here on the quill versus trying to rotate the indicator itself. You can move the indicator back and forth, but you don't want to turn it by grabbing the indicator. Now we're going to first verify if the vise is square to the machine. So the first thing we did was check that the vise was actually tight to the machine. Now we're going to verify that the vise is square to the machine. I can go ahead and tell you it will not be, because I purposefully set it incorrectly. So I'll move my vise toward my quill, or my spindle, or my indicator, however you want to think about it. And always remember, we're moving the table, or the vise, or our part. We never move the spindle. The tool, the spindle, that all stays still. We move around the vise or our part. So I'm moving the vise toward the indicator. I'm going to lower the quill, and I am positioning my indicator near the left edge. The edge that you start from is arbitrary, and the height that you set your indicator at is somewhat arbitrary, but we are going to want to find a path that we can move back and forth so that we don't hit anything. And we know that we have these two counter bores that the socket head cap screws are in, and we don't want the indicator needle to fall off into those. So we either want to go above them or below them. And so I will move back and forth to ensure that I'm not going to hit those counter bores, and I'm not. So now that I have successfully pre-positioned my indicator, now I will move the vise into the edge of the indicator needle, making sure that the correct angle of the indicator needle is held, and that I'm only contacting the ball portion of the indicator needle itself. So I'm going to move the vise toward the indicator needle, and I'm going to watch this face, because this is a very sensitive measurement device, and small motions register large changes on it. So once I get close, I'm going to very carefully and slowly feed the vise toward the indicator until I get about half a rotation from where it was at rest, and I'm going to turn the face of the indicator to where the 0 lines up with the needle. And I know it may be difficult to see that, but the 0 on the dial is now where the needle is pointing. Now I'm going to switch handles, and I'm going to move my X back and forth. And I'm going to move the vise toward me, and I'm going to watch to see if there is a change in the position of the indicator needle. And that's going to tell me, relative to where I just set my 0, how far out the other side is off. Now, if I see this needle starting to move round and round, I can go ahead and stop, and I know that I'm going to have to indicate my vise. If it stays relatively steady across the entire travel, then I can look at the difference and decide whether or not that difference is allowable for the part that I'm making. So as I travel, I can already see the indicator needle starting to turn around, and that means that our vise is not square. So we are now going to go into how to indicate a mill vise. To indicate a mill vise, the first thing we're going to have to do is we're going to have to loosen the vise up a bit so that we can move it around in a controlled fashion. I'm going to use this 7/8 wrench and loosen the vise on either side so you can see I can move it around. If I wanted to remove the vise at this point, I could just take these bolts out and take the vise off of the mill table. Now, I'm not going to bother with that right now, but what I am going to do is I'm going to roughly align the vise just by eye to where I think it looks relatively straight, and I'm going to pick a side that I want to start from. I'm going to, since I'm already positioned here, start from the left side. I'm going to tighten that screw. I'm going to leave the other side loose, but I'm just going to run it down finger tight. Now, from this point forward, we have committed to a procedure because we picked a side to start from, and we're going to go from that side every time. Now, we can stop and restart this procedure from the other side, and I'll show you why you might need to do that in a moment. But for now, we're going to start on this side. I am going to set my 0 to where it is approximately opposite the natural resting place of my needle, and I'm going to dial until the needle stops on the 0. So I'm going to move my vise toward my indicator, and I'm going to pay close attention to whether the needle moves clockwise or counterclockwise, because we're going to use that information in a moment. So as I'm moving the vise toward the front of the machine, my needle is turning clockwise, and I'm going to make note of that. And I'm going to stop whenever it gets to 0. Now I'm going to feed the table across toward me so that the needle moves toward the other side of the vise. Now, as I'm turning this, you'll notice that the needle on my indicator is moving counterclockwise now. That gives me a key piece of information. As I moved the vise toward the front of the machine, my needle turned clockwise. As I'm moving across the back of the vise, now that needle is moving counterclockwise. That means that this side of the vise is further back toward the back of the machine. I hope that makes sense to you, because the only way for this needle to be turning counterclockwise is for this vise to appear to move toward the back of the machine, which means, for a better visual, the vise is sitting on the table like this. Now, that's very exaggerated, but that tells you which direction the vise is out. Now I've stopped before my needle gets back to its home position, because I always want the needle in contact with the back jaw. I know that I want this vise to be straight, and the only way I can do that is to rotate the vise that way. So I'm going to rotate the vise if I'm looking down on it clockwise. It's going to pivot about the nut that we tightened over here on this side. I'm going to use a soft mallet or a dead blow hammer, and I'm going to gently but firmly tap the vise and watch the needle, and we're going to tap it back essentially to the 0 point that we started. Now it may not be perfect, and that's okay, but at this point we're going to move the vise away from the indicator, and we're going to go back to our home start position, and we're going to do this process over and over and over again until we are happy with the level of alignment to the axis of travel. So I'm going to move the vise toward the indicator. I'm going to stop at 0. I'm going to feed the vise toward me. Then I'm going to feed it all the way across to the other side. And I can look, and I am just about 3/1000ths of an inch. So for this particular lab, you should always aspire to have better than 2/1000ths of an inch across this 5-inch vise. So this is not good enough. I can still see that whenever I moved across, the indicator needle moved, but now if I look at it, it moved clockwise, which means that whenever I was tapping it earlier, I must have tapped it a little too much, because now this side of the vise is closer to the front of the machine. And that's why it's important to watch whether it's moving clockwise or counterclockwise. So that means now I need to tap it back in the other direction just a bit, but only by a couple of 1/1000ths of an inch, less than the thickness of a sheet of paper. So I'm going to be gentle with it, tap it back to 0, move the vise away from the indicator, go back to our start position, and verify again. Now, at this point, we should be pretty good, but we have to verify. And we're going to watch to see if the needle moves, and it's holding pretty still. It is at about 1/2 of an inch from one side to the other. That's about as good as you're going to get. At this point, we need to tighten this bolt or this nut. Whenever I tighten it, I don't want to just grab that wrench and pull it. If I do that, there's a high likelihood that I can move the vise. What I'd like to do is I would like to put my reaction hand on the vise itself and use that to help prevent moving the vise. Now, I would not stress if you see this move right now. Go ahead and tighten the vise. And as you can see, when I did that, that needle moved a little bit. But the last step is that we need to verify that we're still square. So I'm going to drive off, move the vise away, go back to our start point, center 0, and then read back across to see if we are still within the constraints that we want to be in. And you get to pick those constraints once you are designing your own parts. How good does the vise need to be is something that you're going to have to decide. For us, we're going to define that for you better than 2/1000ths across the back of the vise. Now if I look at that, it's right about 1/2 thousandth of an inch. That's very, very good. That's 1/2 thousandths of an inch, or 5/10ths of a thousandths across a 5-inch travel, which means that that is out 1/10 of 1/1000th of an inch per inch of travel. That's pretty good. So, at this point, both of the nuts holding the vise down to the table are tight, and it is square or aligned to the axis of travel. Now we could actually use this vise to make a part. There are times whenever you are adjusting your vise and you get to a point and you're tapping on it and you're hitting it, and it's like it gets to a wall, and no matter how hard you hit it, you can't get more out. On the bottom of these vises, there are stops or dogs, depending on what you want to call them, and they sit inside of these grooves in the mill table. Kind of like these guys. They sit down inside of there. And if it turns enough to where it locks up, it doesn't matter how hard you're going to hit it, you can't turn it anymore. So what you would do at that point, if that happens to you, if we were to say that we're in the middle of aligning this thing and I am hitting it and it won't go any further, I would stop the process. This nut would be loose at that point. I would go ahead and tighten that nut and loosen this nut, and now I would start this side of the vise being my 0, and I would do the exact same procedure, only in the opposite direction, and you will then be able to adjust out the rest of the error in your vise alignment that you need. And that's a very, very quick and easy way to do it. I just like to show you guys that little trick. Always remember, the last step after you tighten up both nuts is to go back and recheck that the vise is square after you've tightened everything up, because there is the chance that whenever you tighten it, that it shifts on you, and you need to know about it.